Let's dive into Chapter 8 with Lesson 8.4, Multiply and Divide Rational Expressions. A rational expression is an expression that contains a polynomial in the numerator and denominator of a fraction. We will refer to the numerator as n of x because it's a polynomial, and the denominator as d of x. If you just have a rational expression on its own and you're asked to simplify, the first thing you're going to want to do is factor both the numerator and denominator completely. Because you'll have a factor in the denominator possibly that has a variable, you'll want to state restrictions in our domain. We've talked about this before. When you have a variable in the denominator, remember the denominator can't equal 0. Sometimes we have to work backwards and solve for x. Last but not least, we try to reduce our rational expression if possible. So let's try one. Write an expression that's equivalent to x cubed minus 5x squared minus 24x over x cubed plus x squared minus 72x. The key on these problems is to follow our steps carefully. Step 1, factor both the numerator and denominator. We have x cubed minus 5x squared minus 24x in the numerator. If we think about our factoring review, all three of those terms have an x in common. If we factor the x out, we're left with x squared minus 5x minus 24. Taking a look at what's left over on the inside, x squared, bx, and c, if we factor 24, numbers that go into 24 are 1 and 24, 2 and 12, 4 and 6, or 3 and 8. And 3 and 8 we could work with to multiply and get negative 24 and also add to get negative 5 if we use positive 3 times negative 8. The numerator then factors to x times x plus 3 times x minus 8. If we do the same thing in the denominator, we also have an x cubed, x squared, and x term. We'll take an x out of that, and that gives us x squared plus 1x minus 72. Numbers that go into 72 would be 1 and 72, 2 and 36, oh, we've got a lot of them, 3 and 24, that's a 4, 4 and 18, oops, not 118, just 18. 5 doesn't go in, thank goodness, 6 and 12, 8 and 9. Wow, that's a lot of pairs that go into 72. Can you think of a pair in some way that we could multiply to get negative 72 and add to get positive 1? If we use negative 8 and positive 9, we could make that happen. Therefore, the denominator will factor into x times x minus 8 times x plus 9. That's step 1, 8 and 9. There we go. That's factored completely. Step 2, we want to state any restrictions in the denominator. Remember, by definition, all the values in the denominator, we can't let whatever we plug in for x make that equal 0. So if I set that first x not equal to 0, there's nothing we have to do with that one. If we say x minus 8 can't equal 0, we'd have to add 8 to move it over, and x can't equal positive 8. If we set x plus 9 can't equal 0, and we move 9 over, x also can't equal negative 9. We have 3 numbers for our restrictions, 0, positive 8, and negative 9. Otherwise, x can be anything else in this expression. Step 3 is the fun part. Step 3 is to cancel anything out on top and bottom. That's an exact match. I see the plain x on top and the plain x on bottom. We can cross those off. The x plus 3 in parentheses doesn't match with anything in the denominator, so we'll leave that. But then we have x minus 8 and another x minus 8. If they're the exact same in the parentheses, they can cancel out. The quotient is then what's left over, or our rational expression. All we have in the numerator is that x plus 3, and all there is in the denominator is x plus 9. And that would be your simplified rational expression. Let's try another one. What is the simplified form of the rational expression 4 minus x squared over x squared plus 3x minus 10? All right, step 1, we're going to factor. Notice 4 is a perfect square and x squared is a perfect square. That would be the same as 2 squared minus x squared. And that would factor into 2 and 2, x and x. One's positive, one's negative, so minus and a plus. In the denominator, we have x squared plus 3x minus 10. That's going to be that x squared plus bx plus c rule where we break down the constant of 10. Let's see, what goes into 10? We really only have 1 and 10 or 2 and 5. Out of those two, can you think of a pair in some way that would multiply to get negative 10 but add to get positive 3? If we split apart our x squared term into x and x, if we make 5 positive and 2 negative, that would give us negative 10 when you multiply and positive 3 when you add. So I'll put a minus 2 and a plus 5. There's your step 1. Step 2, thinking about the restrictions in the domain. What values for x make this fraction not possible? Again, it's all about the denominator. Remember, the denominator can't equal 0. If x minus 2 can't equal 0, and we add 2 to move it over, x can't equal positive 2. If we take x plus 5 and do the same thing, say that that can't equal 0, and we subtract 5, x also can't equal negative 5. So we'll just put them in one statement. We'll make that negative though. There we go. There are your restrictions on the domain. From here we try to simplify. And this is where things get a little tricky. Do you see in the numerator how we have the 2 minus x, but in the denominator we have x minus 2? That means that they're not actually the same. So I'm going to take that x, or that 2 minus x term right here, and I'm just going to reverse the order. So if we say that this equals, instead of saying 2 minus x, if I say negative x plus 2, and then I write everything else out, 2 plus x over x minus 2 and x plus 5, what we could do with that purple expression is actually factor out a negative. So I'm going to take that first part, and if you factor out a negative to the outside, that would make negative x become positive, and positive 2 actually become negative. Check that out. And then if I put everything else next to it and down below, now look what happens with those x minus 2's. Now they're a match, and we can cross them off. The negative on the outside just means the numerator is going to have a negative coefficient. So our answer would be negative 2 plus x over x plus 5. And you'll notice I'm keeping these answers in parentheses on the numerator and denominator. You're going to want to stay with that kind of process throughout this chapter. Everything we've covered so far is when you have just one rational expression, but we're going to build on that. It says steps to multiply rational expressions. We have 4 steps, and again, you're going to want to follow these steps in order, 1, 2, 3, and 4 specifically. Step 1, factor the numerator and denominator completely. Well, we've already practiced that. We're just going to have more than one expression to work with. Step 2, state restrictions in the domain. We've already done that as well. Step 3, any numerator can cancel out with any denominator where there's a match. So that will help us reduce our answer. So step 3 is the reduce step. And then step 4 is really not a step, it's just kind of a way to write your answer. Keep your answer in factored form. You don't have to multiply everything back together when you're done. All right, so first, I don't know what I'm saying. First, find the product, not produce. We're not looking for apples, that's okay. Find the product of 2xy over z and 3x squared over 4yz. So the first thing I'm going to do, since we're asked to find the product, is I'm just going to write it as a multiplication problem. 2xy over z times 3x squared over 4yz. We've actually done problems like this before when we worked with exponents. Step 1 is to factor, But if there isn't anything being added or subtracted, step 1 is done. Nothing factors in this because we can't pull something apart from different terms. Step 2, state restrictions on the domain. So the domain means we can't have variables on the bottom that make the bottom equal 0. I see a z, and I know z can't equal 0. And I see a y, and if we have 4 times y times z, y also can't equal 0. Those are the restrictions in our domain. Step 3, any numerator can cross off with any denominator. So if I look at this, if I take a look at the numerator, I'm just going to kind of group it all together. 2 times 3 is 6. X times x squared is x cubed. And then I have a y in the numerator. In the denominator, there's a 4. We have a y and then z times z, which would be z squared. Now, if we want to try to reduce anything on the top and the bottom, I recognize right away that 6 and 4 both have a factor of 2 in common. So I can reduce those. 2 goes into 4 twice, 2 goes into 6 3 times. And then the x cubed, that's going to stay. There's a y in the numerator and a y in the denominator. Those will cross off. And that would give us a total of 3 times x cubed in the numerator over 2z squared. And that's your simplified product. All right, who's ready to kick things up a notch? What is the simplified form of 5x over x plus 3 times x squared plus x minus 6 over x squared plus 2x plus 1 times x squared plus x over 5x minus 10? Wow, that's a pretty big product of rational expressions. Step 1, we want to factor. Let's just take one expression at a time. The first one is 5x over x plus 3. Well, in the numerator, 5 times x, nothing factors, so we'll leave that. And in the denominator, x plus 3, nothing factors out of that one. I'm going to go ahead and put that in parentheses for later. Step 2, x, or the second rational expression, x squared plus x minus 6. So we want numbers that multiply to get negative 6, but also add to get positive 1. 6 breaks down into 1 times 6 or 2 times 3. If we do negative 2 and positive 3, we'd get positive 1 when we add. So that means we're going to have x minus 2 times x plus 3 over x squared plus 2x plus 1. The only way you can multiply to get 1 is 1 times 1. And if we add those, we get 2. That means we'll have x plus 1 and x plus 1, the same factor but twice. In the last fraction, we have to be careful. We have x squared plus x, but there isn't that last number. What that means is really all we're going to get is the option of a common factor. If we factor x out of both terms, we get x plus 1 left over. And in the denominator, 5x minus 10, we could take a 5 out, and we have x minus 2 left over. There are all of your rational expressions in factored form. From here, let's go to step 2, stating restrictions in our domain. Remember, none of the denominators can equal 0. If I look from left to right, x plus 3 can't equal 0. And if you move 3 over, x can't equal negative 3. I have 2x plus 1s, but we don't need to write that out twice. The same value will apply to both of them. X can't equal negative 1. The 5 does nothing to the domain, but the x minus 2 is going to be included as part of our restriction. If I move that 2 over, x can't equal 2. So we have 3 restrictions in our domain. X can't equal negative 3, negative 1, and positive 2. And then finally, step 3, the fun part, let's reduce if possible. Do you see anything on top and bottom that could cancel? I see the first 5, and then this 5 in the denominator. Those cross off right away. That's awesome. The x, though, on the left and the x on the right, they're both in the numerator, so they don't cross off. Let's see. We have x minus 2. Oh, I see an x minus 2 on the bottom. There's an x plus 3 and an x plus 3. We've got those to cross off. And then x plus 1 can cross off with one of the x plus 1s in the denominator. That would make our final simplified rational product. We have x and x in the numerator, which would be x squared, and all we have left in the denominator is x plus 1. That's simplified quite a bit. And I think that's a really good stopping point for us. We'll finish the rest of the notes next week.